If you live in the middle of a major city and turn on your kitchen faucet to fill a glass of water, you probably never think twice about where that water came from. Because somewhere, miles away, a massive municipal utility is running giant treatment plants, booster pumps, and pressurized city mains that push treated water straight through your basement wall. But if you drive just 20 minutes out into the countryside, that municipal grid completely disappears. And instead, over 40 million homeowners rely entirely on a private subterranean system sitting right inside their front yard. Most people imagine a private well as an open, underground lake where a pipe simply drops down like a drinking straw. But the reality of pulling ice-cold drinking water through hundreds of feet of solid granite bedrock is a masterpiece of hydraulic engineering. To understand how this entire system works from start to finish, you have to start with the drilling process. Because before you can ever get a single drop of water into your home, a heavy commercial rotary drill rig has to pound a vertical shaft deep into the earth. The drilling crew sets up a massive mast over your yard, spinning a tungsten carbide roller cone drill bit while pumping high-pressure air and drilling mud down the center of the drill pipe to pulverize soil and gravel while blowing the crushed rock cuttings to the surface. As soon as the drill bit punches through loose topsoil and hits solid bedrock, the crew slides heavy 6-inch steel casing pipes down the borehole, driving the steel shoe deep into the rock ledge to form an impenetrable mechanical seal. This upper casing is crucial because the biggest threat to your drinking water is what is sitting on your lawn, including muddy rainwater runoff, fertilizers, animal waste, and nearby septic drain fields. To ensure none of that contaminated surface water can ever trickle down the outside of the steel pipe, the crew pumps liquid bentonite clay or cement grout into the space between the dirt wall and the steel casing, creating a sanitary barrier that locks the well off from surface pollution forever. Once the casing is securely anchored into solid rock, the drill bit continues downward directly through the bedrock without any casing at all, drilling hundreds of feet deep until it intersects natural water-bearing fractures, creating an underground storage reservoir that holds about 1.5 gallons of fresh water for every linear foot of standing depth. Now, you might wonder why we cannot just put a standard water pump in the basement and suck the water up through a pipe from 400 feet down, and the answer comes down to a fundamental law of physics involving atmospheric pressure. A suction pump sitting at ground level does not actually pull water upward. What it really does is create a low-pressure vacuum inside the pipe, allowing the 14.7 pounds of natural atmospheric air pressure pressing down on the earth to push the water up into the pipe. Because atmospheric pressure is limited, the absolute theoretical maximum height that suction can ever lift water is about 33 feet. And in the real world, with friction losses, a shallow suction pump fails completely once water is deeper than 25 feet. To solve this problem, modern well systems flip the physics completely upside down. Instead of trying to suck water from the top, they drop a heavy, stainless steel submersible pump all the way down into the depths of the borehole so it can push the water upward from the bottom under massive mechanical pressure. A deep well submersible pump consists of a long, narrow cylinder with a high-torque electric motor sealed at the bottom and a multi-stage centrifugal pump assembly stacked directly on top. Inside that pump end, anywhere from 8 to over 20 individual impellers are stacked in series inside diffusers along a central drive shaft. As the motor spins at 3,400 RPM, each individual impeller stage grabs the incoming groundwater, flings it outward with centrifugal force, and adds roughly 10 to 15 pounds of pressure, easily generating enough continuous hydraulic force to lift water 400 feet straight up into your home. What makes this subterranean motor even more ingenious is the way it cools itself in the dark bottom of the well. Electric motors generate intense internal heat, and if you ran a 1-horsepower motor inside a stagnant puddle of water, it would overheat and burn out in just a few minutes. To prevent this, the pump is designed so that the intake screen sits above the electric motor, meaning every single gallon of cold groundwater drawn into the pump must first get sucked upward past the outer stainless steel shell of the motor, acting like a high-speed liquid cooling jacket that whisks away heat continuously. Directly above the topmost impeller sits a heavy brass spring-loaded check valve, which allows water to shoot upward into the delivery pipe, but snaps tightly shut the split second the pump turns off, holding the entire 400-foot vertical column of water inside the pipe so the system never loses prime. As this water travels up the vertical drop pipe toward the surface, it encounters another major engineering challenge known as the frost line. In cold northern climates, the top 3 to 6 feet of ground freezes solid during the winter, and if your water delivery pipe simply popped out of the top of the well cap above ground and ran across the yard, the water inside would freeze solid on the first winter night, bursting the pipe and shutting down your entire home. To prevent this without digging an expensive, leaky concrete well pit, modern wells utilize a brilliant fitting called a pitless adapter, installed directly through the steel casing below the local frost line. The vertical drop pipe holding the heavy submersible pump connects to a brass slide fitting with a thick, precision-molded rubber O-ring seal. When the pump is lowered down the well, this fitting slides smoothly down the inside of the casing along a guide track and drops into the bracket, where the hundreds of pounds of downward weight from the pump and water column wedge the brass surfaces together, compressing the rubber O-ring watertight against the casing wall with 0 threads or bolts underground. The water flowing up the well hits this adapter, takes a sharp 90-degree turn, and flows directly into a flexible poly pipe buried deep in the trench, heading straight through your basement wall safely below the winter frost line. Once that high-pressure water pipe enters your basement, it meets the real control center of the whole house, which consists of a pressure switch and a captive air pressure tank. You cannot simply wire a submersible well pump directly to your faucets so that the pump turns on every single time you rinse a spoon or flush a toilet, because starting a high-torque electric motor dozens of times an hour causes severe electrical stress, overheating the motor start capacitors and burning out the contacts in short order. Instead, the well pump works in partnership with a pressure tank that stores pressurized water on demand, utilizing a fundamental law of physics known as Boyle's law, which states that while water is virtually incompressible, air can easily be compressed like a mechanical spring. Inside a modern pressure tank sits a flexible butyl rubber bladder that completely separates a pre-charged pocket of compressed air on top from the water chamber below. When your well pump turns on, it forces water into the bottom of the tank, expanding the rubber bladder and squeezing the captive air cushion on top into a smaller space, which causes the pressure inside the tank to rise steadily. Mounted directly on the brass tank T-pipe is the pressure switch, which acts as the automated brain of the whole operation. This switch contains a small, flexible rubber diaphragm exposed to water pressure on one side and calibrated steel springs on the other, wired directly in series with the 240-volt electrical line feeding the pump. In a standard 40-60 setup, as soon as the expanding air bladder pushes system pressure up to 60 psi, the water pressure snaps open the electrical contact points, cutting power instantly. When you walk upstairs and turn on your shower, the well pump does not turn on right away. Instead, that compressed air cushion inside the pressure tank acts like an invisible hydraulic piston, pushing stored water out of the rubber bladder and through your pipes at a steady, silent 40 to 60 psi. As water leaves the tank, the air expands and system pressure gradually drops. The moment the pressure falls to 40 psi, the calibrated steel springs inside the switch snap the electrical contacts shut, instantly firing the subterranean pump to refill the tank and supply continuous water to your fixtures. Sizing the tank properly ensures that your deep well pump runs for at least 1 to 2 continuous minutes every time it starts, which keeps the motor properly cooled and drastically extends its operational lifespan. Before this well water reaches your drinking glasses, it passes through dedicated water treatment systems to remove dissolved minerals and fine sediment. The water first flows through a 50-micron sediment filter to catch any coarse sand particles, followed by a whole house water softener. Inside the water softener tank sit millions of microscopic polystyrene resin beads charged with sodium ions. As hard groundwater containing dissolved calcium and magnesium carbonates flows across these beads, an ion exchange reaction takes place, where the resin beads capture the hard minerals and release harmless sodium ions into the water, eliminating hard-scale buildup in your water heater and copper pipes. Finally, the conditioned water passes through a high-intensity stainless steel ultraviolet disinfection chamber, where powerful 254 nanometer UV light penetrates any passing microorganisms, instantly scrambling their DNA so they cannot reproduce or cause illness. When an entire home depends on a single automated well system, understanding failure modes is the key to preventing plumbing emergencies. One common hazard is a waterlogged pressure tank, which happens when the internal rubber bladder tears over time, allowing the compressed air charge to dissolve directly into the water. Without that compressible air cushion to act as a spring, the water pressure drops from 60 to 40 psi the split second you open a faucet, causing the pressure switch to click on and off rapidly like a machine gun every 2 seconds, which can overheat and destroy the subterranean motor in under 48 hours. Another critical failure mode occurs during summer droughts if the regional water table drops below the pump intake screen, causing the multi-stage impellers to spin dry without water and melting the plastic diffusers in under 2 minutes. From the deep fractured granite bedrock hundreds of feet beneath your lawn, through multi-stage centrifugal impellers and liquid-cooled motors, up through freeze-proof pitless adapters and compressed air bladder tanks, and finally through automated ion exchange softening and ultraviolet sterilization, your private well system operates as a self-contained, high-pressure utility right in your own yard, quietly delivering hundreds of gallons of pure, crystalline water to every faucet in your house with the exact same reliability as a multi-million-dollar municipal grid.